Thanks so much, Rich, for that very kind introduction. And also thanks to you for everything that you've done to help advance my career through the years. You've been very important to me in that way. So I thank you for that. And thanks for the opportunity to speak to your group today about a topic that I think is quite interesting. And I hope that you all find it as interesting as I do. So right off the bat, let's just talk about conflict of interest. And I just want to let you know that I have no relationship with the IBM Watson here, but I mean, you might say there's a little bit of a resemblance, but there's no conflict. So, let's discuss a bit, what is artificial intelligence, how it's going to influence sleep medicine, how it is influencing sleep medicine, and what is this going to mean for us in medicine a bit going forward? I mean, so I'm going to try to touch on all of these questions. And I'm not going to tell you how to feel about it, but I will ask you to think about it, because it's really going to impact all of us in our careers in medicine, regardless of our specialty. So what do we mean by artificial intelligence? Well, it's a branch of computer science that deals with the simulation of intelligent behavior in computers. And so it's essentially the capability of a machine to imitate intelligent human behavior. Machine learning is basically the process by which this is accomplished. And then computational phenotyping is a way to use biomedical informatics to identify certain patient populations. So we'll touch on each of these topics as we go through the talk this morning. So we know in medicine, we capture trillions of data points and trillions of waveforms every year. And you can see some examples here. You have polysomnography, you have EEG studies, EKGs, any kind of waveform would fit this. We do somewhere around 25 million sleep-wake EEGs every year in the US. We do about 4 million polysomnograms every year in the US. And so there's all of these waveforms that are really visually interpreted by human eyes. And we've been pretty successful doing that for decades. What artificial intelligence is beginning to show us is something that I think is exemplified by this picture here. You might think that this looks like the trail the last time you went for a walk in the temperate rainforest of Olympic National Park. And you'd probably be pretty right with that thought. However, if you look more closely, you can see other things in this picture, such as a tree sloth up on this tree. You see a panther here, a cougar over here. You see an orangutan in the middle and an elephant over here. And there's probably other things that I still haven't appreciated in this picture. And so the point being that when we're visually interpreting these waveforms, there are aspects of sleep microstructure, time and frequency domains of this microstructure that artificial intelligence can examine and actually give us some pretty deep insights that before we really weren't appreciating. And consider this as well. We focus on DNA so much, but each of us has 3.2 billion DNA base pairs, and that can be encoded by 2 bits or 800 megabytes for the entire genome. And the genome is relatively static with the exception of mutations or post-translational modifications or methylation, epigenetic related methylation of DNA. But but in general, it's static. And what your genome doesn't really tell you is all those environmental exposures that are out there. Did you drink toxic water? Did you get badly injured in a fall, etc. And so the point being that by some estimates right now, your physiologic state, when combining your environment and your physiology along with your genetics, contains roughly 1 million trillion times more information than resides in your genetic code. So this is what artificial intelligence can allow us to do. If we think that the EEG, we could potentially be called the encephalome as we begin to understand it better, that there's a lot of things in there that are indicative of your current physiological state that can be actionable for medicine. So real quick, just start out with this. we do polysomnograms, and which involve measuring all kinds of different parameters. And this gets scored by a sleep technologist right now. Now, the problem with that is that, inter-score reliability is not that great. And that's what this slide shows here. If you look at the epoch by epoch percent agreement, and this would be just in sleep staging here, the more of these sleep technologists, this is beyond sleep staging. This also involves, in blue, hypopneas, which are respiratory events. In yellow, you have obstructive sleep apnea, and in orange, central sleep apnea, in red, arousals, and in blue, periodic limb movements and sleep. You can see the more that you ask people to agree on these things, the less agreement there is. And so that's just a product of the rules that we've made to score sleep studies and, the fallibility of human scoring. Artificial intelligence is beginning to enter this area, and this slide here shows an F measure on the y-axis, which is a high fidelity measure that combines sensitivity and precision. And then on the x-axis, you have all the sleep stages, non-REM being N1, N2, and N3, and then REM sleep. And MS1 is manual scorer 1, MS2 is manual scorer 2, AS1 is auto scorer 1, and AS2 is auto scorer 2. And those are the artificial intelligence auto scores. And the takeaway here is that you can see, when you compare MS1 to AS2 or MS2 to AS1, in other words, you're comparing the machine learning to the human scoring, that there's a pretty high F measure across the board, with the exception of N1, which is often difficult to differentiate or can be challenging to differentiate from wake. So artificial intelligence is beginning to be able to score sleep studies pretty accurately. And this is also shown here. Biswal and colleagues took it a step further, and they look at sleep staging, apnea detection, AHI categorization, and limb movements. If we look at the confusion matrix in panel A on the left, sleep staging, you can see we have human scoring on the y-axis and then prediction on the x-axis. The prediction is the AI prediction. And you can see that there's pretty high agreement across the board, again, with the exception of perhaps differentiating between N1 and, in this instance, N2 sleep. For apnea detection, you can see the coefficient of determination is high, comparing predicted AHI by artificial intelligence versus true AHI is determined by human scoring. For AHI categorization, we define an AHI, or an apnea-hypopnea index, which is a number of respiratory events you have per hour. If you're less than 5, it's normal. 5 to 15 is mild, 15 to 30 is moderate, greater than 30 is severe. And if you put people into those bins and you compare AI to humans, you can see, again, pretty high agreement, particularly in the moderate and severe, more severe sleep apnea ranges. And even in the mild range. There's a little bit of a challenge around differentiating between no sleep apnea and mild sleep apnea. And then lastly, for limb movements, again, the coefficient of determination is high between AI and human scored sleep studies. So really showing that this is going to happen, and it's going to be in many ways to the betterment of sleep medicine, that we're going to have a new, I think, gold standard for scoring sleep studies, and it's going to be done through artificial intelligence, which is going to free up our technologists to come and work with us in the clinic in order to help our patients, with their PAP treatment adherence and other issues. So I think it could be a win all the way around. Let's pivot away from that to considering whether artificial intelligence can estimate sleep apnea severity just by the EEG. And so this is really taking the EEG to another level. In this study done by the group at ENSO Data in Wisconsin, they looked at over 4,500 individuals who had a PSG. They just looked at the EEG, and they considered these global phenotypic features that they derived from the EEG. And, and then they use that to look at things like respiratory cycle related EEG changes, and applied a lot of different machine learning models. wanted to determine whether or not, just by looking at the EEG, if you could tell whether somebody had more moderate to severe sleep apnea or milder sleep apnea or no sleep apnea. In other words, the cutoff was an apnea-hypopnea index of 15. At the top, that's sleep stage architecture. That is essentially called a hypnogram. So you can see 0 is going to be wake, 1, 2, and 3 are N1, N2, and N3 sleep, and 4 is REM. So that's the sleep architecture of somebody who's considered to be low risk for AHI. You can see the number of arousals per epoch there in the middle of the slide, and then lastly, the respirations per epoch. And if we compare that to what was found for an individual to be estimated high risk for sleep apnea, you can see that there's many more arousals and awakenings and fragmentation in the hypnogram at the top. There's more arousals per epoch, and there's more respirations per epoch. And so they were able to come up with a sensitivity, specificity, and accuracy of 86.9%, 99.5%, and 91.1%. And, since specific tests rule in diseases, this is certainly would seem to indicate that the EEG has potential to potentially, through AI, diagnose sleep apnea without the need for any other elements from a PSG. And at the very least, it could screen somebody for sleep apnea. So all these EEGs that we're doing, there could be an indicator whether or not a patient needs to be referred to a sleep specialist. Here you can see the receiver operating characteristic curve on the bottom left, where you have the true positive rate versus the false positive rate. So true positive would be sensitivity plotted 1 minus specificity, and you want the ROC curve to be as high as possible to the upper left corner. In this case, this is a nice looking ROC curve. Yeah, these researchers have also been able to apply machine learning to predict a CPAP prescription pressure within 2 centimeters of water. So CPAP, continuous positive airway pressure, this pressurizes the airway to treat sleep apnea. A lot of times in the past, we would do PAP titration studies and then select a pressure. And what they're showing here is that artificial intelligence, looking at variables like body mass index and oxygen desaturation index and apnea-hypopnea index, is able to predict pretty well, what somebody's ultimate PAP pressure is going to be. So artificial intelligence may not only score sleep studies, it may not only be able to provide a sleep apnea diagnosis just from the EEG, but it could help us decide how to apply our treatments. And I think that's going to be true in medicine in general as we apply artificial intelligence to our specialties. They also looked at treatment adherence here, and the things that predict adherence are the things that we would imagine they would, such as how much snoring there is, how long their apneas are, how sleepy they were, how bad or how severe their oxygen desaturations were, and so forth. What about mortality? This is a random forest analysis of 5-year all-cause mortality. These researchers looked at over 1,500 physiologic variables. So these were 435 clinical variables from the electronic medical record, along with over 1,100 polysomnography variables. And they applied multiple machine learning algorithms to this data as well. And this is the predictive utility ranking for this analysis. And what this basically means is how important each one of these variables is to making these predictions or to the final result of this analysis. And of course, you would imagine, blood pressure is number one, and that makes a lot of sense. But you can see there's a lot of sleep variables that are pretty high here, such as sleep efficiency, which is the percent of time that you're in bed trying to sleep that you're actually asleep, percent of time with your oxygen saturation below 95%. So, that's not that low, but that seems to be important here. Other things such as sleep time, how long you slept, how long it took you to fall asleep, how much wakefulness you had after you fell asleep, all those things were important to this analysis. And if we look at the receiver operating characteristic curves again, you can see that when you combine the clinical variables with the polysomnography variables, you get the highest area under the curve. And so that is shown here. This random forest analysis showed an ROC area under the curve of 0.82 with an accuracy of 77.4%, precision of 86%, and a recall of 78%. So this, this computational phenotyping, I think, has opportunities here for us to leverage artificial intelligence in clinical and polysomnography data to answer some pretty stunning questions, such as 5-year mortality. So when you consider all of these things here, and if we just focus on the EEG, this is just kind of a framework in which to consider artificial intelligence. And so you have the various data levels there on your left, and the EEG probably fits somewhere between clinical and biologic, with pathophysiologic in the middle. It would fit somewhere in there. And ultimately, it could end up being a biomarker for, like we just discussed, obstructive sleep apnea, perhaps narcolepsy, other sleep disorders, insomnia, biomarker of death, potentially. So I think artificial intelligence is going to get stronger and stronger, and we're going to learn more and more from the tests that we're currently doing in order to advance healthcare and take care of our patients. Now this topic you guys are going to be interested in, I think, and you may be aware of it already a bit, but
Nate, should we stop? Anybody have that was fascinating. Anybody have questions on that first half that Nate about AI and how it's really changed how they're approaching this? Anybody? I know Nino, we have a group that, of course, are neurophysiologists that study this sort of stuff. Nino, you have questions?
Nate, this is fascinating. These computers, are you using UDAP computer? Is there like a computer core that processes all this information? And are these programs that we could use, for example? Or are they available commercially?
Yeah, I mean, I can put you in touch with the group that I'm working with at Enso Data in Wisconsin. Mm-hmm. I can't tell you the exact details of the computing programs that they're using. That's a bit beyond my level of expertise. Mm-hmm. But this group is certainly up for collaboration. So send me an email and we can have a conversation.
So Nino,
and I have a question.
We have two questions, Jeff and Frank.
Okay.
Jeff.
Jeff. Yeah, I just wanted to follow up on that question. There's a whole group in computer science at the University of Washington that are leaders in this type of work, primarily working with EEG and motor behavior. Would be people like Raj Rao and the others in computer science. My question for Nate is, I know John Miller and Shaheen Hakimian have done a lot of work on over the years on intracranial recordings in sleep. And I wondered if that was something you had any comments on, or can give us direction, since we do have a lot of that data here just down the hall from you. And then the second question on that is anything you can briefly comment on the development issues. In other words, whether anyone thinks these measures would work in younger kids.
Yeah, I mean, I think we have had some conversations with Dr. Hakimian in the EEG and epilepsy group, and I think that there are opportunities to look at intracranial monitoring and potentially examine that area to help localize seizure activity further, to help differentiate between non-epileptic and epileptic seizures, and better understand the influence that sleep has on the occurrence of epilepsy. A lot of times when we bring patients in the epilepsy monitoring unit, if they're not having any seizures, we sleep deprive them for a period of time in order to trigger these events. And I think we know that can work, but our understanding of exactly how is a bit thin. So there may be opportunities there as well. What was the second part of that question?
He wants to know if he can
development. Yeah. Younger kids. In other words, how young do you think that what you're doing is relevant
Oh,
too? Or
I think, yeah, I mean, it could
since
be.
we make these diagnoses pretty young sometimes.
Yeah, I think we could apply this to younger children and even neonates. I don't think there's any limitation to the opportunity to really explore the EEG more deeply, across the lifespan. So again, we can have conversations to try to look into that if you all have some ideas that you want to explore.
Good, sounds great. Frank, you had a question too. Sorry, Nate, I didn't mean to slow you down. You threw a lot of interesting stuff at us early on.
Yeah, this is exciting, and thank you, Nate, for this talk. Is very fascinating. And I was just going to add a comment from what Jeff has said. We in our lab, and we are collaborating with Horacio at the University of Washington and applying artificial intelligence on our animal EEG, and trying to identify, trying to score sleep using artificial intelligence, and in fact, even trying to detect the epileptic form mathematically in the EEG. And those are some of the projects we are doing there. But I'm also interested in what you said is, it seems like so far the studies that you presented, they are looking at applying artificial intelligence on only one modality of the polysomnography. I wonder if they have a way where they incorporating all the data, not only the EEG, but respiration and the others, muscle activities and retinography or something.
That's a great question. I mean, they're beginning to look at the EEG and actually be able to tell oxygen desaturations from the EEG.
Oh, wow.
The other elements of the sleep study can be included as well. You know, some of them can be noisier and have less applicability. But I do think that there are opportunities to integrate different data sets. For instance, I think what we're learning is that the EEG is the most important part of the sleep study from this perspective. But, if we're able to extract clinical data out of the electronic medical record and integrate it with that, then things get vastly more powerful. So, working with entities that have, massive databases, some of these insurance companies and self-insured employers that have all of this type of information, provides opportunities to kind of merge the clinical and the polysomnographic elements together in order to give us a more powerful understanding of sleep health and disease. And so I think maybe I'll continue here.
Yeah, please keep going. Sorry.
So the brain age, no, it's my pleasure to answer this question. So is basically the difference between chronological age and what a person's identified brain age is. And so that's the brain age index. And, currently we're able to identify this via MRI. So there are all these diseases here, Alzheimer's, schizophrenia, epilepsy, traumatic brain injury, that MRI studies are able to look at and begin to come up with this notion of excess brain age. And so these researchers used a machine learning model to try to capture this notion of brain age just from the EEG. Here on the left, you can see on panel A, you're comparing brain age on the y-axis to chronological age on the x. And you can see that you get a mean age difference of 23 years. Now, this is just looking at sleep macro structure, and you can see that there's a pretty wide variability there. But on the right, if you look at sleep microstructure in the time and frequency domains, you can see that things tighten up pretty dramatically here. This slide is kind of complex, but it's worth going through. If we look at the rows, we have young people up here, middle-aged in the middle, and then older individuals at the bottom. If we look along the diagonal here, you can see that these are individuals, the lucky individuals whose brain age is less than their chronological age. In the middle, these are individuals whose brain age matches their chronological age. And then at the top are the unfortunate individuals whose brain ages are older than their chronological age. And so again, you can see there's a hypnogram at the top of these individual patient representations, and then you have a spectrogram at the bottom. And I think what you can appreciate perhaps is that, you know, the area around 13 to 15 hertz is much more well defined. And this is kind of like the sleep spindle range in those that had a healthier or younger brain age than those with an older brain age. And then perhaps even more importantly, if we look at the covariates here, you know, the things that we think would result in a healthier brain actually do result in a healthier brain. So N3 sleep, deep non-REM sleep, so the amount of time you spend there and the percentage of time that you spend there predicts a healthier brain age. A better sleep efficiency predicts a better brain age, as does more sleep and more N2 time. On the flip side, you know, disturbance index causes brain age to be higher. More light sleep during your sleep causes an older brain age, and then more wake after sleep onset. So the things that would indicate sleep disruption are indicating an older brain age. And if we take this another step, you can see here we have the probability percent on the x-axis, and then the brain age index, which is your brain age minus your chronological age. And if these researchers looked at those that had significant neurological or psychiatric disease compared to those that didn't, and you can see the histogram represented by the red line is shifted to the right in comparison to the blue line. And this is about 4 years. So this is kind of a proof of concept that those that have the neurological disease, their brain age index is unhealthier, as would be expected. And we see a similar finding here in panel B, looking at individuals with hypertension and diabetes compared to no hypertension and no diabetes. And again, we see a shift of the brain age index to the right, indicating an older brain in those that have more diabetes and hypertension. So really, you know, taking it a step further to show that this analysis, it does indeed correlate diseases that would affect brain health, showing that increases brain age. So let's pivot now and just kind of think about what it means for sleep medicine, medicine in general, and for, you know, us in society. Couldn't talk about artificial intelligence without putting up one of my favorite movies here, which is The Matrix. And for those of you that seen it earlier in the movie, Neo, the protagonist, is offered a red pill or a blue pill. The blue pill would allow him to just go back to ignorant bliss, and the red pill really shows him the world that he's actually living in. And I think artificial intelligence is causing a bit of a reckoning in sleep medicine because, you know, we don't have enough sleep specialists to take care of the sleep burden of disease that's out there. We have about 1 sleep specialist for every 45,000 Americans. And those of us that are out there are concentrated in urban areas. And so there's massive swaths of the country that don't have any sleep medicine expertise. But, you know, if artificial intelligence allows us to do our jobs more smoothly, you know, if an artificial intelligence chat bot can be used to contact a patient and let them know about their study results or what the next steps are going to be or things like that, you know, physician extenders, things that can allow us to be more efficient with our time, and also to redeploy staff if we're not scoring sleep studies by hand anymore. You know, those things really offer opportunities. But, you know, the future the future is going to probably look different. And, you know, doctors are conservative and they get scared of change. And so, you know, the sleep medicine community just has to ask themselves, I mean, are they going to circle the wagons and protect the status quo, or are we going to embrace the future? And, you know, we'll see how this plays out in the next 5 to 10 years. Another thing I think about a lot, I mean, we've lived in a time of genetic determinism for quite some time. where we feel like, so much of who we are and what we do and how we behave is just genetics. But, now we're moving into this era of the quantified self where, we want to measure everything about ourselves and understand everything about ourselves. And so, if we know our genome deeply, and if we're able to quantify ourselves deeply, I just get worried about this notion of phenotypic determinism. I mean, for instance, 20% of the population is shift workers. Shift work is essentially has been labeled a carcinogen. But you would have to imagine that some people would be more susceptible to the carcinogenic effects of shift work than others. And, there may be a moment in the future where we can figure that out before somebody has the job. Well, somebody may be prevented from getting a higher paying job because they don't have the right genome. They don't have the right phenotype. And that could be a problem. So, we just have to think about where all of this is leading. And, as we rumble down the tracks with these advancements in artificial intelligence. I would make a brief comment here about these consumer sleep technologies. I get asked about this a lot in my clinic. And the reason that this is appropriate to discuss here, I think, is that, these are beginning to provide really big data on a population scale, objective data about sleep that can then be leveraged to understand sleep better. For instance, Sleep Score, which is an app. Actually, the app was developed at the University of Washington. I was one of the co-inventors of that. If you go in the Apple iTunes stores, you can get Sleep Score. I would encourage you to have a look at it. It turns your phone into an active sonar so it can measure fine and gross body movements at night and then put it through an algorithm to determine sleep stages and sleep quality. And in fact, Sleep Score showed around COVID, people were sleeping sleeping longer, and probably in large part because a lot of us aren't commuting anymore. And we have more consistency now as a society between weekday and weekend sleep times, which is typically what would indicate a healthier sleep schedule. So, these things are big data. They're showing us, they're answering big questions. I put this up here just for your interest. As far as determining sleep, Fitbit and the Oura Ring are the best, with Sleep Score a little bit behind them. Wakefulness is best determined by Sleep Score. Light sleep is best determined by the Fitbit Charge 2. Deep sleep best identified by Sleep Score. And then REM by Fitbit Charge 2. So I think Sleep Score and Fitbit Charge 2 are right now the two best ways that we can assess sleep in our home, typical home environments. So one thing about artificial intelligence I'm really hopeful is going to do for all of us, it's going to take us back to the future. I mean, nowadays, between electronic medical records and documentation and dealing with insurance companies and all of this stuff that gets between us and our patients, I think a lot of that could be stripped away. So here's a picture, a Norman Rockwell picture. The doctor's leaning in, he's making eye contact, he's discussing the problem with the child's parents, and their needs are being met. They're feeling cared for in the moment. He's not typing on a computer while he's asking these questions, which is what we're encouraged to do in clinic right now, unfortunately. Well, you know what? In the future, I would imagine in our clinic room, we'll have a conversation with our patient. We'll be making eye contact. And while this is happening, the note is being generated, and you have a probability index of various diseases with recommended tests. And perhaps the note could suggest specific keywords that have to be in there to satisfy the patient's insurance company to get her the testing and the treatment that she would need. And so I'm really hopeful, if artificial intelligence is applied to medicine in a way that brings us closer to the holistic care of our patients, then I think it's been deployed correctly. And I don't see any reason why this couldn't be our future. So, just in summary here, we define machine learning, AI, and computational phenotyping, and spent some time talking about how artificial intelligence is going to be scoring our sleep studies going forward. And that's pretty much, I think, a given. You know, the EEG, time and frequency domain aspects of sleep microstructure is really going to crack things open. And this is very interesting to me because we've been in a time of diagnostic reductionism in sleep medicine. You know, we do these home sleep apnea tests now. They don't even collect the EEG. We're just monitoring your ability to breathe at a time that you're telling us you're asleep. And so while this is happening, you know, we've been moving farther and farther away from the EEG, and then all of a sudden, boom, here we go. It appears that it's much more important in a sleep study and in the diagnosis of sleep disorders than originally anticipated. So we'll have to see, you know, and track and follow how that develops. We're going to need ways to measure EEG in a reliable way in an ambulatory setting, I think, in order to really have the full impact of this out there. Because as I mentioned, there's so few sleep doctors out here. But if an artificial intelligence company has an ambulatory EEG arm and they can get a couple of nights of EEG and then use that to provide a diagnosis, it might be a way to have all this happen without the need of the sleep specialist. And then you just have the sleep specialist take care of the most severe cases. This is how we can expand access to care for people. Artificial intelligence can also help with treatment decisions, and such as the PAP prescription accuracy work that's been done, the computational phenotyping and 5-year survival. And you know, it's quite interesting to imagine how artificial intelligence will be able to look at everything in your chart and then some of these gathered physiologic variables and maybe come up with really accurate assessments of what your future looks like. And so we have to imagine what are the psychological ramifications of that for people going forward. The brain age issue, I think, is really important as that continues to be developed. I think that's fascinating and would certainly be a way, you know, if we could have an easily accessible brain age index, you know, then we can go back to our patients and see if the interventions that we're giving them to treat their neurologic disease is improving their brain age or not, or if their behaviors are making their brain age worse. You know, I think that would be very powerful motivator for people to change their behavior. If you can point specifically to say, hey, you know, your brain is less healthy now because of X, Y, or Z, or more healthy because of something that we've done to treat a disease. Talked about the consumer sleep technology accuracy and just this notion of the quantified self and how that's going to continue to develop. And I think, you know, more and more as these things become more sophisticated, you know, more healthcare is going to happen in that area. For instance, we know cognitive behavioral therapy for insomnia is the best treatment for insomnia, but so few people do it. Well, you know, Pear Therapeutics is creating an app that will allow a patient to have cognitive behavioral therapy through the app and not have to try to seek out a person who knows how to do this, which there's just not enough people, and the burden of insomnia is so massive. So that's just one example of how these technological developments are advancing the care of patients with sleep illness. And then just talked about the implications for the future. And I'm sure, I mean, you know, if you guys think about in neurosurgery, all the different ways that this may well change the way that you do your jobs, you know, I'm sure a lot of that is going to be very exciting, but it's also going to challenge a lot of preconceived notions about how things can, you know, are done and how they have to be done. And so we all have to, I think, approach this future with an open mind in order for it to be as beneficial as possible to our patients. And with that, I will leave you with some of my favorite movies related to artificial intelligence